So how did Hertz produce electromagnetic waves? Well, basically the production of electromagnetic waves is due to the fact that charges create electric fields around them, and changing charges, right, current, generates magnetic fields. So what you can do is oscillate a current. And in the book example, you have a long straight wire with an AC power source that turns the long wire, the top positive, the bottom negative, and then flips it at some frequency. So when you vary a current, you vary the associated electric fields and magnetic fields, and those electric and magnetic fields propagate away at the speed of light. So since you're altering the field, and that field, the strength of the field moves away at the speed of light, you create an electromagnetic wave. Now, how quickly you oscillate the current determines the frequency of the wave. The wavelength is determined by the fact that frequency and wavelength are related to the wave speed, and for electromagnetic waves, the speed of light is wavelength times the frequency. The speed of light is fixed in a vacuum for an electromagnetic wave, 3 times 10 to the 8 meters per second approximately. So the frequency of oscillation combined with the known speed of light, you can calculate what the wavelength of light is going to be. Now, a couple of caveats when creating electromagnetic radiation, right? You're oscillating the electric field because you're changing the charges as with time. You're changing the magnetic field because you're changing the current with time. So the electric field, shown here with an E and a bar on top, and the magnetic field, shown with a B, remember magnetic fields are represented as B fields. The E fields and B fields, the electric and magnetic fields, of an electromagnetic wave vary perpendicularly to the direction of wave travel. In other words, electromagnetic waves, or EM waves, are transverse waves. So we talked about transverse and longitudinal waves last semester, just as a very rapid reminder. Longitudinal waves, if you imagine a slinky that's stretched out, longitudinal waves are compression waves. So if you push the slinky in and pull it out, that compression wave travels through the slinky. Sound is a longitudinal wave. As I speak, my vocal cords are vibrating the air, vibrating the molecules. Those vibrations go into your ears, your eardrums, excite the hairs in there, and cause oscillations, which you hear as pressure waves. Those are longitudinal waves. Electromagnetic waves are transverse waves. They're water waves, similar to water waves. They're similar to a slinky that you oscillate up and down, and that wave, the peak, moves down the slinky. So they're very perpendicular to the direction of wave travel, and they're perpendicular to one another, which means that, let's pretend the direction of wave travel is to the right here on the screen. The electric field might be going up and down like this as it travels to the right. If that's true, then the magnetic field has to be going like this, 90 degrees. So the electric field's on a plane, a vertical plane, going up and down like a dolphin going through the water. If that's true, if the oscillation is vertical, then magnetic field has to be perpendicular to both the direction of travel and the electric field. So it's like a snake slithering horizontally forward. And again, the electric field doesn't have to be vertical. I just use that as an example. Whatever direction the electric field is in. So let's imagine this is the direction of the electric field. Here's our magnetic field in blue. So if the electric field is vertical, the magnetic field has to be 90 degrees. But if the electric field changes, the magnetic field is still perpendicular and can also change. But they have to be perpendicular to one another, and both have to be perpendicular to the direction of travel. Additionally, the electric field and magnetic fields vary sinusoidally. Again, they vary like a sine wave with the same frequency. So if the electric field has a slow frequency, the magnetic field has that same slow frequency. It's not like the electric field is jumping up and down and the magnetic field is going really slow, and I cannot do those things at the same time. I challenge you to do that at the same time, 2 different speeds. And they're always in phase. So when the magnetic field peaks, the electric field peaks. When they're both zero, they're both zero. When the electric field is at a minimum, magnetic field is at a minimum, and so on. The strength of the fields are also related by the speed of light. So if you know the strength of the electric field, you can use this relationship to calculate how strong the magnetic field is. Again, this is the peak. Well, this relationship always holds. So if the electric field is 0, the magnetic field is 0, that becomes undefined. But the peak electric field, the maximum value of the electric field, and the maximum value of the magnetic field can be found via this equation. So the production of electromagnetic waves is basically an oscillating current. So if you think of modern radio antennas, or the antenna in your car, right? The antenna nearby that are broadcasting your radio channels, FM and AM channels, and we'll talk about those in the next video, send very, very tall, usually on high places. They send signals up and down, creating a frequency, generating a frequency that spreads out at the speed of light. Those electromagnetic waves excite your car antenna. Now, most modern cars have car antenna that are hidden away in the windshield or in the rear window. But back, again, 70s, 80s, and earlier, the antenna was literally a metal antenna that's stuck up out of your car. So what happens is those electromagnetic waves sent out by the radio station excite the electrons in the conductor in that antenna, causing them to oscillate at a certain frequency. You turn your car radio to the appropriate frequency that you want to create a standing wave in that car antenna that reinforces the wave, giving you the radio signal into your amplifier, sending it to your car speakers. So a distinction. Radio waves are light. Sound waves are sound. Sound waves are longitudinal waves, but radio waves, we think of radio as sound, but radio is light. We communicate at times via radio communication. The large radio station antennas are sending out light. They're sending out electromagnetic radiation that your car or your radio sees and then converts into a sound.